Good morning, everyone, and welcome back to our CNC Turning Techniques channel. Today we continue our tutorial, and once again we're talking about powered tools. As you can see from the image behind me, today we'll be focusing on keyway slots. It's a simple thing because it essentially becomes and remains a programming task that's almost two axes, and it's probably the operation that will be most requested when we work on lathes with powered tools. So, first of all, let's make a very brief yet concise and comprehensive introduction regarding the zeroing of direct powered tools in detail. What does direct mean? We generally, typically speaking, normally have two types of powered tool holders in our machines. The geared ones, meaning those with the cutter or positioned horizontally, and the direct ones, which have the cutter positioned vertically, are two distinct types of tools. They're called direct because they take motion directly from the turret's drive shaft, while geared ones need a bevel gear to transfer the motion and rotation at a 90-degree angle, which is a significant difference. So obviously when we talk about keyway slots, we'll have a powered tool that mounts a cutter in this condition to secure the cutters effectively and efficiently. Our powered tools use ER type collets, and there are R25, R32 and R40 collets available for different applications. Essentially, R32 means a collet with an external diameter of 32 millimeters, and R40 means a collet with an external diameter of 40 millimeters. The type of turret on the tool holder determines the choice of collet, which is crucial for proper tool function. When we talk about Japanese machines, for example, the BMT turret type, like the BMT 75, can mount the R40 collet and can also mount the R32 collet, providing versatility. Obviously, when we have a BMT 75 turret, I don't know if you're familiar with the connection of but it's important to understand its capabilities. The turret has information that might not be relevant for programming, but it's good to know. The attachment of the turret, poorly sketched in my drawing, looks something like this. Here are the 4 fixing screws. I trust that you've opened your eyes a bit. Basically, my turret is made like this. I'm looking in this direction, where I place my tool holder, and I see this. When we talk about BMT 75, it means that this hole has a diameter of 75 meters. Then there's the BMT 65, which has this hole with a diameter of 65 meters, and so on. Normally, on larger turrets, we can mount tool holders with R40 collets, and smaller. We can't do the opposite, meaning if we have a machine with a BMT turret, I can't remember where it starts, BMT 45. That uses an ER25 collet, mounting a 32 or 40 is difficult. But if you find the tool holder that allows it, you can do it. It's obvious that we would be working beyond the machine's capabilities. It is obvious that we will be working above the machine's capabilities. This has nothing to do with programming. I don't like to explain something more with programming. Instead, it relates to how you zero the mills. Normally, when we talk about direct tools, the mills are zeroed once and only once when you buy the machine, and then there are small adjustments. Why is that? Because the rotation axis of our mill doesn't change. It's always the same. So the 0 point of our mill will be exactly in the center of our rotation axis. How do we determine it? If we're lucky, we have our zeroing arm, the one shaped like a cross. We take our mill and touch this point, and if our mill has a diameter of 10 millimeters, we zero it by telling it Z5. We measure it, whether it's a fan or whatever. We'll say Z5 because our center will be shifted by 5 millimeters from the contact point. Automatically in our tool table, a value will be written that You zero it by telling it 5. We'll say Z5 because our center will be shifted by 5 millimeters from the contact point. Automatically in our tool table a value will be written that could be, for example, 112.0. Could be, for example, 112.0. Every time we mount a candle cutter, we can directly write this value 112.032 in the tool table. The X value, however, needs to be done each time depending on the extension of our cutter. You can zero out in Z as many times as you want, but it's a waste of time. Zero stays at the cutter's axis center. Program with this in mind. If you then mount a 3 diameter cutter, the zero will always be in the center of the cutter's rotation axis. Program with cutter center. Keyway on shaft 6 mm cutter. Ignore tolerances, chamfers. Activate C axis M35. Cutter TLO5 Position coolant on. Move Z10 2 mm from 30 mm shaft. Let's imagine we're going to make this keyway on this shaft using a 6 mm diameter candle cutter for this specific task. Let's not think about tolerances or anything specific right now, and let's not worry about chamfers. We'll think about tolerances later. In this particular scenario, I'll tell you how to handle tolerances for keyways and slots with the C axis at this moment. For now, let's create a simple program following what we learned in the previous tutorial in our current setup. So the first thing we need to do in our program is activate the C axis. So M35 activates C as we proceed. Let's see if switching to green makes it a bit clearer, because this black is a bit tired. Otherwise, we'll go back to black in this demonstration. Today, we're using a nice colorful board. As we continue, then we call our tool, let's say TO505 for our 6 mm diameter cutter in this example. Yes, I think it's clearer now in this case. Then we position ourselves quickly, turn on our coolant, and our shaft has a diameter of 30, so we go to 34. Physically 2 mm away at Z10, because our cutter will position itself with its, I don't want it to fall, with its center of rotation at this point. When we correspond to our quota, it's crucial to ensure that the self-centering chuck is properly secured. This is important because an unsecured chuck can lead to inaccuracies in the machining process, potentially damaging the workpiece or the machine itself. To secure it, we activate the locking hole. In this case, the weak one is more than enough. This step is vital as it ensures the stability of the chuck during operation. After securing the chuck, we proceed to start the spindle. We use the same spindle code with P12, which allows the machine to interpret it as the rotation of the motorized axis. This step is essential for synchronizing the spindle's movement with the machine's operations. Then we use G1, G94, F100 because we are working with X as 30 minus 3 times 27, no, times 24, because we need to read this as a diameter. The calculation here is critical. 3 millimeters we have, here too. 30 minus 3 equals 24, so X 24. It's important to ensure accuracy in this calculation to avoid errors in the machining process. Make sure to choose an end mill that can handle drilling. Some end mills don't handle full entry well, so you need to enter this way. The selection of the end mill is crucial as it affects the quality of the key slot. Be careful with the end mill you choose when making a key slot. We stay in G1 and go to Z40 at F150, 200, 300, depending on how you set it, 200. This command is important as it dictates the movement of the tool, ensuring precision in the machining process. This should be established based on the type of end mill, the number of cutting edges you have, and the number of revolutions. A couple of simple calculations, and you'll find it. If you don't feel like doing the calculations, just call the end mill supplier and tell them, I need to remove 3 millimeters of depth with an end mill on a C40 that can handle the turning. They'll let you know. If they don't, then change suppliers. So, what was I thinking of telling you? Right, minus 40, because we have a slot of 30. We go to minus 40 because that's the absolute quota, meaning the distance from my 0 point on the end mill, which is the center, to the 0 point of the piece, which is usually on the machined plane, the farthest from the self-centering chuck. Then total. X32. Let's not do it in G0. Let's stay in G1. Maybe let's put a F400 on it. And we exit our part. At this point, we can set our G0 to X300, Z300, and stop the spindle. The spindle will stop like this, but probably all the other CNCs need to know what M5 refers to in this case. So P12, and we reposition our machine around. You see, we did this milling. We got close to our milling cutter. We approach our cutter slowly. We move forward in the work. We lift slowly, and we come out quickly. We made a beautiful keyway. This program works great when we have a standard keyway. So a keyway that doesn't have particular tolerances. Sorry, let me check something. Yes, everything's okay. When we have a keyway where the tolerance is plus or minus 0.03, things change, especially if they tell us to break edges. This means that if it's like this, the operator who will mount our shaft in any machine could cut their fingers. So often they want us to create small chamfers. In these conditions, ideally, we would have a machine with a y-axis. But we're unlucky. We don't have it. And we have to manage both the tolerances and the chamfers well. We always rely on this program, which we will repeat 3 times with some small corrections. Why 3 times? Because to make a keyway like this, with chamfers and tolerances, we will need 3 end mills. Never think you can maintain tight tolerances with an end mill that starts at full depth. You'll maintain it for 1 piece, 2 pieces, 3 pieces, and because to make a keyway like this with chamfers and tolerances, we will need 3 end mills. Never think you can maintain tight tolerances with an end mill that starts at full depth. You'll manage. To maintain it for 1 piece, 2 pieces, 3 pieces, and use a 5.5 end mill as before. Create chamfers with a 10, 4 or 8 diameter end mill, or 10 with 3x45 chamfers. Start with a 5.5 end mill. Create chamfers using a 10, 4 or 8 diameter end mill, or a 10 with 3x45 chamfers. Pass the end mill over the key at a depth of 26 or 27, based on chamfer size. Finish with a 6 or 5.99 diameter end mill. Ensure a reliable supplier. If tight, lock the end mill in R40 or R32 collet to run eccentrically. Use a weld and shank for finishing. Check online for weld and shank details. Modify the previous program if tight tolerance is hard. Focus on programming. Diameter 4 or diameter 8 or diameter 10, with chamfers 345, and you'll use your end mill to pass over your key at this depth in the same direction. So the program is similar, it only changes the depth you'll be working at, which will no longer be 24 but will be 26 or 27, depending on the size of the chamfer you want. Then you'll need to do a finishing pass with a calibrated end mill of diameter 6, or better yet, 6 minus 0.01. You'll need to have a good supplier who provides you with the correct material. It's not easy. A little trick: if the end mill is tight, you'll lock it in R on the R40 or R32, meaning in a collet, with a thickness of 1/100th. This will allow the end mill to run eccentrically by 2/100ths and expand better. For finishing, use the Weldon type shank. The Weldon shank is a pinned connection where there isn't a collet that closes but a screw that tightens it in a ground diameter. So go check online what a Weldon shank is. Do the finishing with the Weldon shank. Another little trick, and I'll deny having told you this because heaven forbid the designer finds out. If you really can't maintain a particularly tight tolerance, we can modify the previous program. So how do we modify it? Let's just write the part related to the programming. G T4 100X T4, approximately 40 F150, which is CH001 repeated 8 times. F200, not C, sorry. H and that's it, not C. I told him something silly. What is this nonsense? This causes our end mill to move forward. The C axis shifts by 1/100th of a degree, and it could be 10/100ths. Calculate it. It goes back and passes one of the two sides. This skill is necessary to keep tolerances slightly in line, which means that if I cut the keyway too much, we won't have parallel sides, because the C-axis goes back. So even if there is evidence in the video, I will deny saying this, but it can be a method to expand a keyway out of tolerance when you don't have the C-axis within a couple of hundredths, because otherwise this situation worsens and the part is not acceptable. So if you have tolerances of about 3/100ths, you can handle it. The best, however, is to have a precise end mill that enters safe parameters, redo the previously roughened keyway, side with a 5-5 or 5-8 or 5-9 end mill, depending on what you find on the market, and have the correct tolerance on the finished part. Thank you for being with me. If you liked the video, please give it a like and subscribe to my channel. Thanks a lot, and see you next time.